We've discussed a system to define electromagnetic structure at the source, known as polar coordinates from an observer. As the plane pitches upward, the XYZ axes associated with it tilt and roll as well. This coordinate system can be used to draw any atom as it is rolling around in free space. Now consider what is actually received. As the atom rolls around, light is given off and expanding outward as the electrons bounce in and out, forward and backward, at various trajectories in the electron cloud. The coding emitted is coming in lighted blobs at distance intervals so fast that all we pick up is the distances between blobs in a constant beam. This is what is coming at us through the machine's measurements. Now we have structure to compare to the structure of the atom. What can we see? A machine called a spectrometer focuses at your object and picks up light coming off of it in various wavelengths. The light emitted is identified as the atomic emission spectrum, unique for each element in the periodic table. Each wavelength that has a reading is measured for intensity, recorded in a machine called a spectrum analyzer. You see the element is becoming a line, but not so fast. The line received is observing different wavelengths at the same time, so actually they are on top of each other. The intensities for each wavelength remain and the pattern repeats. First the longer wavelengths at their intensity, and then the shorter wavelengths on top of it at their intensity. Now we have a workable line. Most writing equations of a curved line is done integrating derivatives known to be zero at each turning point. So when a squiggly line goes from turning up to turning down, the equation at the inflection point is found by integrating a 0-second derivative. Engineering is so obsessed with derivatives, trying to describe faster and faster turns, they didn't learn a slightly different way to perform integration. Line integration uses an arbitrary observation point and draws a straight line to the squiggly one. Another straight line is drawn for each tiny segment of the squiggly line, which also adds up to describing the curve. This is done without taking a single derivative, which is good because finding the derivative is not always easy. In the case where there's so many turning points in the emission spectrum received, line integration is really the only way. So the line integral of the structure, a geometric combination of mass and charge enclosed, is the same as the line integral that's received by that structure, as it is received in a duration of time. We would effectively draw and integrate a line that couldn't be understood with an equation that is the lowest derivative possible. Now how do we find it? The slice inside the pyramid is the beginning of structure for an object. It is the portion of the plane that lines up with the rolling coordinate axes. The line to the slice is solved in terms of aperture of the eye, estimated pitch, roll, and yaw of whatever structure is built as it changes in time. Also in terms of distance d to the center from your starting point A. That's the good news. Different time-dependent orientations represent different elements in the periodic table of the elements from chemistry. It's a guess that this compares to chemistry phase diagrams, where the area inside the pyramid above and below the cross-section represent different phases, solid, liquid, and gas, that the element can possibly experience. The thickness of the cross-section is its stability at the ambient phase. As you look through a microscope or as you traverse along an orbit using a telescope, the grid lines point to the center of the object for reference. What we're really inspecting in this illustration is a small arc of a whole circle rotated about the center. When you observe an XY graph, what is most typical when learning mathematics, you are looking flat at four quadrants: positive x with positive y, negative x with positive y, negative x with negative y, and positive x with negative y, respectively. Technically, there are 8 quadrants because all of those can sit into the page as well as out of the page. So there's 8 blocks in the shape of a cube. Recall the enclosed chemical illustration. The individual slice dips below the axis as you rotate the pyramid about the corner. Half of the slice during rotation falls into the page, into the negative z. We don't have to concern ourselves with this at this point, because geometry draws it, and so does the math. So let's give ourselves a break and stay in the positive x, positive y, positive z quadrant. A special sliver within that quadrant is pictured. As you focus on the center through the microscope with your right eye, the coordinates line up with that center along a distance d. At the same time, you're also viewing both sides of the slice. That's 3 points of reference in a single snapshot from point A. Your left eye is doing the same thing, lining up with the eyepiece, looking straight down at the center, and also at the same two sides of the slice. That's point B. Notice in a microscope that the two eyepieces point straight down in two different trajectories to arrive at the same point in the slide. This is done by using mirrors within the scope. So the angle between them is known as a function of distance to the center of the microscope slide. Or in the most general case, the central black hole of a galaxy. Here, distance isn't known, but the reference tilts at the x and y axis can be estimated. The equation is left in variable form because at different scales, the pieces of information we can be sure about are different. Galaxies are slow moving, while up-close smells are given off and travel very quickly. Galaxies matter because they represent a portion of nature that moves slowly enough to observe structure in the emission spectrum. Electrons bounding around an atom are too jostled to regard, but a galaxy maintains the same pattern over long periods of time. Before we rush to throw out supermassive black holes, consider the predicament. Look at the illustration and reduce the slice to near zero. Look at all the lines that have to be perfectly described in order to even understand a black hole, each totally unique yet reducing to nearly the same line as they draw closer and closer to the central point. And this drawing is exaggerated to show that the lines are different. In distant black holes, points A and B are so close to each other, parallax angles, for example the slower changes in a distant forest as you drive quickly down the road, described as parallax, were completely abandoned pretty much as soon as people started looking up. Astrophysicists explain a radius just outside the black hole as a point when things start making sense to them. Let's for a moment gloss over the fact that this pinpoint, at great distance away, is itself thousands of light years thick. It is no surprise that astronomers described the confusion as best they could, even wrongly, because the alternative is to say that we have no idea what goes on in a black hole. Relax, it's covered here in the material. We know enough from the illustration to see that there are multiple points of interest along the same line of sight, blocking each other from a solid view. There's the point on the slice as well as the point behind that on the xy plane, conveniently staged at 90 degrees to your initial view at point A. This reference plane is there to identify the tilt axes of the slice. The xy plane is for A only and doesn't line up at 90 degrees from point B, which is the next issue to discuss. For now, we can be happy that the diagram is enclosed, meaning there are no lines veering off the page. Every line drawn has two endpoints, and each point is connected to another line, completely enclosed within the page. That's an important distinction, because it means that the geometry is manageable, meaning that all unknowns can be described in terms of the rest. So what are we contemplating? The goal is to describe the slice from 2 points, A and B. The logical scenario is to ask where they meet, and the answer is along the line of sight for both of them. That's the point of interest, the target, the object of preposition, and the thing we know the least about. After all, the point is moving, and the size of the cut observed inside the pyramid is dependent on how close that point is to your eyes, A or B. As the point gets closer to the eye, the area of the cross-section looks bigger. The pyramid grows. If you cross your eyes, the two images or edges that you have to compare grow further apart. If you look at a star in the distance, very small differences between the eyes need to be observed to get a reading, because the slice is so small. So as we compare the variety of shapes formed by this illustration, we gain knowledge about individual angles and individual lines one by one in terms of the knowns, until we finally describe the line of sight to the object, be it a fungus on a petri dish or a star on the outskirts of a distant galaxy. What happens on a line is equal to what is received along that line. Our perception of what is received is an accumulation of the events along the line leading up to the observation. Engineering is far ahead with the advancements of flying drones and hybrid cars, but flying saucers are right around the corner. Chemistry is far ahead with the advancements of physical chemistry from quantum mechanics, and we know most of the impactful reactions between elements in the periodic table, at least that energy is transferred from before to after. But what happens during the reactions is still a mystery. Biology is far ahead on how to keep a human body healthy, but safe medications still elude us. In my opinion, pretty good is not yet great. The choice is ours to attempt the geometric challenge. Here's the door.